Hi everyone, this is representing enthalpy changes. So you don't have to write this part down because we already have it in a previous note, but I just wanted to remind you what enthalpy is, and that's the amount of energy either absorbed or released from the system in a particular experiment. So we're just going to look at 4 different ways we can represent this information. The first way is we can put it as part of the reaction. The second way we can represent it as to write it beside the reaction. The third way is we can come up with a molar enthalpy of usually the first reactant in the problem, although you could really find molar enthalpy for any of the entities. It's usually for the first reactant. And then lastly, as a graph. And we're going to see all of these 4 ways incorporated into other parts of our lessons in this particular unit. So method 1 is pretty straightforward. If it's exothermic, heat is being produced, so we're going to write it as a product. So I'm going to use a generic equation for our examples here. 2x plus y makes x2y. I'm just going to add my arrow because this program that I'm using doesn't like arrows apparently. And again, the key here is that if it's exothermic, I'm going to write the energy term as a product. That means that vice versa, if it is endothermic, energy is going in to the reaction. That means energy is a reactant, and I'm going to put the energy term as a reactant. It doesn't really matter if it's the last reactant or the first reactant. The placement of the energy term makes no difference. Method 2, also pretty straightforward. So the delta H is essentially just written to the right of the equation, and it's just important to indicate whether it's endothermic or exothermic by using the according sign. So 2x plus y makes x2y, and then off to the side I've just written delta Hx as a separate piece, and I've used a negative 100 kilojoules indicating that it would be exothermic. If it was endothermic, I would simply write it as positive 100 kilojoules. The third reaction, or third method rather, is a little bit tricky, and it's not tricky insofar that it's a lot of math, but it's different from the first 2, and that's why it always gets mixed up. So really, you don't really need to do a lot of math because the math is easy, but it's based on this formula for enthalpy, which we've already seen. The method 3 is asking us to express a delta Hx, so a molar enthalpy, for the first element in the reaction unless otherwise stated. Most of the time you can do this math just by looking at it, although if you weren't sure how to do it, again we could go back to this formula. So let me show you how it works out, but typically I go right to the final answer on a question like this because you really don't need the math here, but let me show you how it works. So we know that 2x plus y makes x2y, and I've just shown you method 2 here to work from. To turn this into a method 3, I want to know the delta Hx, or molar enthalpy, for the first ingredient. So I want the molar enthalpy for X, which is the first ingredient. So using this formula, and again, you're going to see why you don't really even need to bust this out, but to use this formula, if I want the delta Hx, I'm going to bring the n over to the other side here. I'm solving for delta Hx. The delta H is given. It's negative 100 kilojoules. Here, there are no moles separate, but what we do is we use the coefficient in the balanced equation. So this is the coefficient, and it's always going to be worked out this particular way. So you can see here, this is why you don't really need to bust out the math, but what you do need to is think about how do I want to present this final answer. So the way we're going to write it out is the delta Hx of our ingredient. So our ingredient, our reactant here was just called X. So delta Hx of X equals negative 50 kilojoules per mole. So this is actually the only thing we need to write. We don't actually have to show the math here. You can if you wish to, but really this is all I need for a method 3. Method 4, it's a little bit funny looking here. Method 4, I'm going to show you both the exothermic and the endothermic. So method 4 is a graph. So over here on the y-axis we have potential energy. That's stored chemical potential energy. And at the bottom we have reaction progress, which is the same really as saying time. If it's exothermic, I have my reactants up here, which I just write out. they start with or store a lot of energy. Exothermic means they release the energy. So I start with higher energy, it comes out as 100 kilojoules of energy of product. So my product is lower than my reactants because part of the product is this energy. The gap that I've created here, and you can see I've used an arrow here, is the enthalpy. So we don't have to actually put any numbers on the graph. We're just going to keep it simple like the one I've shown you here. However, if I did have numbers on the graph, that's how I would read the enthalpy. I would just look at the numbers between the reactants and the products, and the difference between them would show me the enthalpy. So going in the opposite direction then, if I have an endothermic reaction, I start off with low energy for my reactants, I put energy in, energy is absorbed, and then they, of course, would end up with higher energy as products. So that's how it works, and again, it's just the shape of the graph as we go. So let's try it on for size. So I want to know the combustion of propane, and the combustion of propane produces 1500 kilojoules of energy. I'm going to do two things. In part A, I want to write the balanced equation and state whether it's endothermic or exothermic. This is going to be important because if I don't have that straight, I can't do the four methods because the four methods rely on a balanced equation and it relies on me knowing whether it's endothermic or exothermic. So once I've done that, the second thing I will do is I will write it out in those four different ways. So starting with the first one, I want you to pause here and then you're going to show me what you know after that. So we just did a problem not too long ago with propane. And again, if you're not sure what a formula looks like, just Google it. So we've got C3H8. Same thing, you might not remember what combustion looks like, but Google it, you'll find it. So we have to add oxygen to propane to make it burn. And if you remember from grade 11, we always assume combustions are going to be complete, which means just carbon dioxide and water vapor, unless we're otherwise told. And lastly, we're going to balance. I balanced the carbons first, then the hydrogens, and lastly the oxygens. Because it's combustion, if we think back to our marshmallow lab, it's going to give off a lot of heat. That's why we burn things, to heat our homes, to heat up in a fire, for instance, something like that. So because it's giving off heat, this is going to be exothermic. Now that I've got all these pieces of the puzzle, now I can go back through and start going through method 1, etc., until I've got all four pieces aligned. So in type 1, all I have to do is add the enthalpy value as a reactant or a product. Because it's exothermic, I'm going to produce heat or exit, or the energy is going to be exiting as a product. So all I'm going to do is I'm going to add my 1500 kilojoules. That value was given to me in the problem. I'm going to add that as a product. So that's a type 1. In a type 2, once again, I have my balanced equation, and type 2 says bring the delta H to the side and use the appropriate sign. So again, because it is exothermic, I'm going to show it as a negative 1500 kilojoules. Type 3 is the one that confuses everybody, but it's not as hard as it looks. Remember, I'm looking for the delta HX of the first ingredient. That's what I'm looking for. So if I go back to type 2, I'll just use it as a scan, or even actually, let's go back to the top in purple. The first ingredient is the C3H8, and I know that it is going to make 1500 kilojoules, or negative 1500 kilojoules since it's exothermic. There's only 1 mole since I have no number in front. So if I were to use my delta H equals N delta HX, I have negative 1500 divided by 1 mole according to my coefficient here. So really, again, I don't really need to bust anything out here in terms of the math. I'm just going to write negative 1500 kilojoules per mole. So nothing crazy there. So type 4, I'm making my graph, so I'm just going to put in my axes. I'm going to put EP here and reaction progress down here. Because it's exothermic, I'm going to start with a high amount of energy, and I'm going to end with a low amount of energy. And the difference in energy is that delta H value, which in this case is 1500 kilojoules, and it is negative 1500 kilojoules because it's dropping. My initial ingredients are my, let's put those in yellow, C3H8 plus my 5 oxygens. And then down at the bottom, we have our 3 CO2s and our 4 H2Os. I'm just going to extend that blue line there. And that's our type 4. So we're going to try one more, and again, I really want you to consider trying it by yourself first, and then so pausing the video and then coming back and attempting to and looking at the answers and seeing how well you did. So this one is when nitrogen gas reacts with oxygen gas to make dinitrogen tetraoxide, 11.7 kilojoules of energy is absorbed. Write a balanced equation and state whether it's exo or endo, so we need to make sure we've got that straight in our head before we do anything else, and then show the 4 different methods. So same technique as the last question, so pause now and then come back and check. So according to the words, I've just converted it into a formula, so N2 plus 2 O2s makes N2O4, and I decided this had to be endothermic because energy is absorbed, which again was stated in the problem. So now my job is to go through the different types, so let's set them up. So type 1, we're going to add the energy as a reactant or a product. Because it's endothermic and energy has to be going in, I'm going to add my 11.1 kilojoules as a reactant. In a type 2 scenario, remember I'm just bringing the enthalpy over to the side, and then I'm writing it as either a positive or a negative. Because it's endothermic, I'm going to write it as 11.1 positive kilojoules. Type 3, I've just rewritten a type 2 above here to use it, but type 3, remember, is we're going to use the molar enthalpy of the first ingredient, so delta HX of N2, and we have the delta HX, we have the moles, and we're just dividing one by the other. So we're going to have positive 11.1 divided by, that's kilojoules, divided by our coefficient of 1 mole, which means it'll only be positive 11.1 kilojoules per mole. And lastly, we're going to set up a graph, again, keeping in mind that it's endothermic. So we start with low energy for the reactants. It's going to increase by 11.1 kilojoules to come up with products of N2O4. And that is all. So try these questions at home so you know what you're doing. And again, we'll see all of these later on in different capacities.